welcome to all of you on this online talk series, Current Trends in Physics. And we are very happy that today we have Dr. Divyendu Nanda as the speaker for the fourth talk of this online series. And he's going to talk about known as dark matter. So, and Dr. Divyendu Nanda is a very active researcher in the field of particle physics and cosmology. Now, working as a postdoctoral researcher at Korea Institute of Advanced Study, Seoul. So, with this, I would like to thank the speaker, Dr. Divyendu Nanda, for agreeing to our proposal for giving a talk on this current trends in physics online talk series. And this brief introduction, I would like to start the session, start today's talk. And before proceeding actual talk, I would like to request my colleague, Dr. Santanu Kaur, to give us a brief introduction of the speaker among the participants. Santanu, over to you.
Thank you, Debapat. First of all, I would like to welcome all to this lecture series, the fourth lecture of the series. I welcome Dr. Divyendu Nanda, who is here with a very interesting topic on dark matter. Why does it matter? So we have heard about different types, very different one, that is dark matter. So I hope the session will be very interesting, and we will have to learn a lot. Means we'll get to learn a lot from him. Anyway, before starting the talk, I'd like to give a brief introduction of Dr. Nanda. He completed his PhD from Tezpur University, Assam, and his PhD degree from IIT Guwahati. He has also completed 1 year of postdoc at the Indian Association for Cultivation of Science, Kolkata. Presently, he is a postdoctoral fellow at the Korea Institute of Advanced Study, Seoul, South Korea. His research area is dark matter and cosmology. So looking forward for a very interesting talk. So I would like to hand over the screen to Dr. Nanda. You are welcome.
Hi. Okay. So thank you very much for this so nice and detailed introduction. So let me share the screen. Can you see the screen now?
Yes, it's visible.
Okay. Yeah. So I also want to thank Debabrat for this invitation to give a seminar here. So I'll try to tell you a story dark matter and why a large fraction of particle physicists are interested in studying dark matter. Why is it so important to know about dark matter? So, but I'll skip most of the mathematical details because that will take a lot of technical details and mathematics. So I'll mostly tell you, how exactly we have convinced ourselves that there is something called dark matter exists, and what are the possibilities or what are the different ways we can try to detect dark matter and try to know more about the particular form of matter. So, if you can stop me at any moment if something is not clear to you, and I'll try to explain again. So I'll basically try to answer or try to explain these three questions. The firstly, how do that there is dark matter? What are the observational signals, or how exactly scientists convinced themselves that there is dark matter in the universe? And then the next, if we convince ourselves that there is something called dark matter exists, then the next question is, what is dark matter? What are the details of this particular form of matter? And unfortunately, so far we don't have any specific idea about exact nature of this matter. But what we really know is that what is not dark matter. I mean, we don't know what is dark matter, but we know what is not dark. So I'll try to explain these things and the relation between these three questions. So the story begins, I mean, almost 90 years ago. This is astronomer who was from Switzerland. So he was interested to know total mass of a cluster of galaxies. So a cluster basically consists of many galaxies, and of course a galaxy consists of many stars and planets, different kind of solar systems. So he wanted to know the total mass of a galaxy cluster. The name of the cluster was Coma cluster. So scientists, he used two different methods for that. So in the method one, the technique he used, which was really dependent on the matter which he can see through his telescope, and the second one depends on something called theorem. Maybe many of you have already familiar with this theorem. So what he did, so he had a telescope like almost 90 years ago. So he used a telescope to observe the Coma cluster and to count the galaxies in that cluster. And then we already have some idea about the typical mass of a single galaxy, because if you have a galaxy for a long time, you can measure the luminosity of that particular galaxy. And from the luminosity, there are some theoretical procedures in astrophysics by you can calculate the mass of that particular galaxy. So now, if you can count the number of galaxies in that cluster, and you know the mass of a single galaxy, then obviously you can find out what is the total mass of the total mass of the cluster, right? So you have to multiply the number of galaxies with the mass of a single galaxy. So the typical mass of a single galaxy is approximately 10 to the power 8 to 10 to the power 10 times solar mass. So if you just do this simple calculation, you will find that the total mass in the first method, it will be approximately 1 times 10 to the power 45 gram. Now, being a scientist, he wanted to check whether it's really true or not. So he used a technique to measure the same quantity again. So he used virial theorem for that. So what is virial theorem? Virial theorem states for a self-gravitating galaxy cluster or any self-gravitating object which already reached some gravitational equilibrium, that means there is nothing coming in or going out from that system. So now if you want to measure the velocity of any object within that system, kinetic energy have to be equals to the half of the potential energy. So this is the usual formula which is known as virial theorem. Now this kinetic energy, which is so what he actually did. So this kinetic, you can you can see the writing, right?
I can see the writing.
Okay. So you can simply see that this kinetic energy will be half mv square, so which will be approximately proportional to this g m by r. So this v and this m and this r, they are basically related. So it will be approximately where times r by g. So now, if you can measure the velocity of an object in that particular gravitational object or in that cluster, and you can also measure the distance r from the center of the distance from the center of that particular object. You can measure v, you can measure r. We already know what is the value of g. So you can also calculate what is the value of m, or what is the total mass of that object. Now, what he found in the second method, that it was 6 times 10 to the power 47 gram. So you can see these two, the ratio between these two methods are approximately 400 times. So that means in the second method, the total mass he got, that 400 times more than the one he got in the method one. Obviously, it was like 90 years ago. So the present techniques or present instruments are much more sophisticated. So the actual value is now around 6 times. So the total mass in the first method and the total mass in the second method, they differ by 6 times. So why the difference was there in these two methods? What is the basic difference between these two methods actually? So the first method was completely dependent on the number of counts. So number of galaxies he could count during that time. So if you miss some galaxies, or if some part of the some galaxies doesn't really emit or talk to light, which is known as photon, then obviously you will miss them through the telescope. And in the method, it was not dependent on whether you can see those galaxies or not. It was completely dependent on some theorem called virial theorem, which depends on the total mass of the galaxy. It does not matter whether you can see or whether you can't see them. So the basic difference between these two methods is that the conclusion of these two this observation was that there is something which does not talk to photon, which does not talk to light. That's why he missed them in the first method, but he included them when he considered the second one. Of course, it has mass, so it will contribute in the total mass of the particular of the object. So he basically named it. I mean, he was the first person who introduced the phrase called matter. By dark, it doesn't mean that it's black or something. By dark, it means there is a form of matter which is missing. So it's also known as missing mass problem of the universe. Now, people really ignored this idea of dark matter for a long time. I mean, approximately 40 years from Zwick's observation. And then in 1970, Vera Rubin, she was an astronomer. So she was interested to find out the orbital velocities of some galactic objects. Now, what do I mean by that? So if you consider the solar system, the sun sits at the center of the solar system, and all the planets evolve around the sun in their own orbits. Now, if you want to know what is the velocity of different planets, or what is the velocity, how the varies from the center of a solar system as you go away from the center, so you can simply use the Newtonian mechanics, right? So you can simply use half of mv square equals to gm by r, and you can calculate what should be the velocity. As you know, the most of the mass of our system is concentrated into sun, and we already know the distance from sun to different planets. You can easily find out what are the velocities for different planets. And if you plot them, you will see this kind of behavior. So as you go away from the sun, the velocities will be smaller and smaller for the planets which are far away from the sun. Now, if you use the same technique, or if you use the same idea for a galaxy, or if you now he was interested to find out the velocities of some stars which are which are far away from the center of these galaxies, like these red points. So now the question is whether the same formula what we have used to find out the velocities of those planets, can we apply the same formula here, and can we see the same? I mean, whether if we apply the same formula, and whether we will observe the similar phenomena or not, or similar behavior of the velocities or not. So expectation, if you're going away from the center of a galaxy, the velocity should decrease by following the Newton's law. But what she observed is that the actual velocities, or the observed velocities, are not matching with expectations. So she found the velocities increases fast as it was expected from the Newtonian from the previous discussion, but it also, when you go far away, it's not falling anymore. It also almost becomes saturated. So how is it really possible? So the only way to make it possible is that if this m, or the total mass of the is not concentrated is not considered as center. Rather, it's like the whole. There are many particles or many different form of which is everywhere, but these are not talking to light. So that's why you cannot see them and you cannot include them in your calculation. So why you are putting this mass m, this is not constant at any distance away from the center. Rather, it's a function of r. So the more distance you are covering from the center, the more mass you are including into your calculation. And then if this m depends on r, if m increases with r, you can see that this will be a, like r dependence will cancel and it will be a constant value. So that's what our conclusion also, that like there are some missing form of matter which you cannot see through the telescope, but they're still there and they contribute to the total mass of the system. That's why this whole behavior was not matching with expectations. And so this was the second observation, which was really conclusive, that there was something, some form of matter which is missing, and it contains a large amount of it contributes a large amount of energy into our universe. And then it started, or then the physics community started to take this seriously. Many observations after that, but the most convincing one after 1970, it's not cluster. So I can I'm showing a video, you can see that first, and then I'll just try to explain what is bullet cluster, how exactly it gives you some information about dark matter. Yeah. Yeah, so what you can see is that there are two different represents two different things. You can see now in this spot that there's some red colors at the center and the blue which is from the center of these two galaxies. So these are like two clusters which were colliding between themselves, and some part of them were much more interactive, and some part of them were not talking between themselves. So what do I mean by? So these red lines are basically red spots, which consists of the usual ordinary matter we know, and they have the ordinary interactions we are familiar with. But the blue regions, they are not actually interacting at all. You can see again, they are not interacting. So they're just passing between without having any interactions. This also gives you the same hint, like there is some form of matter which are not interacting with the visible part of our universe or the visible particles, but they still contribute to the total amount of energy in our universe. Now, how do we know that these two blue spots were there? So this red region, the observers or the experimentalists, they basically mapped this whole collision into ways. This red spot, which came from the X-ray observations. Now, you already know that X-ray, gamma ray, the visible light, all these things are some form of light, some form of photon. So that basically means you can see them with our normal sense of visibility, or normal we can see them through telescopes or different kind of other observation techniques. But these blue spots, these are not coming from some visible form of light. These are coming from something called gravitational lensing. So that gravitational, that was discovered by Einstein. So that technique depends on the fact that if you have some heavy mass, it can bend the light. Now, that basically means there is some form of I mean, in the space that there is a huge amount of mass which you cannot, I mean, you cannot see through the normal light. That's, but if there is something behind that particular form of mass, then that I mean, the light from that source that can bend, and it can come to your come to the telescope, and it can help you to gather some information about. So again, you can see this here. What do I mean by this? Yeah. So that's how light normally travels in a straight line. Now, a very massive object, it can be visible, it can be any form of matter. It doesn't have to be a star, it doesn't have to be a galaxy, it can be any form of matter, but it have to be heavy. That's the condition. It have to be really, really massive. And if light coming away from this particular massive object, light will bend like a lens. That's why it's called lensing. It's happening because of this, I mean, because of the space-time, I mean, curved nature of the space-time, but actually this total gravitational energy of this particular object, it helps to bend this light. And you can put it scope at this point. Sorry, it's not visible. So you can put your telescope and you can see this bending light, and then you can that how much it's bending, that will give you more and more information about this object, which helps it to bend. So that these three observations basically convinced scientists to believe that there is some form of matter which doesn't talk to light, but they contribute gravitationally to all these observations we have explained. So the three observations, all of them are dependent on the gravitational interaction of that form of matter. I mean, without gravitational interaction, don't have any idea about this. I mean, about the dark matter. How does it interact, or how does actually it evolve through this through the evolution of our universe? Then the next question is, how can we gather some information about dark matter, or what is dark matter actually? So to answer that, we first have to understand what are the fundamental building blocks we know already. So what I mean, what are the basic building blocks of a star, of a galaxy, of human beings, of anything we can see or anything we know of? So the fundamental building blocks, by the word fundamental building blocks, I mean, like, if you want to build a house, you need a brick, right? So that's a building block of a. So similarly, the whole universe have to build out of some very, very fundamental particles. So all of us, like human beings, solar system, galaxies, any kind of objects you can see in this whole universe, that's made out of the same quantity known as atom, right? It's now the atom consists of electron and nucleus. And you already know the nucleus consists of proton and neutron. Now, if you go further and further, if you break a proton or a neutron, you will find that you can break a proton and neutron, and you can see that they are consists of something called quarks. Now, you cannot break quark anymore. Quark are the fundamental particle of an atom. So basically, an atom consists of quarks and quarks and electrons. So these are the two fundamental building blocks of our universe. So anything you can see, like as I said, from the human being to galaxies or galaxy clusters, so solar system, everything is made up of this proton, neutron, and electrons. So now the next question is, these are the building block of the universe we can see. These are the building blocks of the visible part of the universe. But dark matter made of? Okay, so sorry. So this thing has this electron, quark. These are known as elementary particles. Now, what is dark matter made of? I mean, is it also made out of these particles, or it's made of something else? Now, as I said, so it interacts only gravitationally. You cannot see it through telescope. You cannot gather any information through ray or any form of light. That basically means it has to be chargeless. It cannot have electromagnetic charge or electric charge, as you know. Electron have, proton have. It cannot have any electric charge. Otherwise, if something has electric charge, that interacts with light. So that's why we cannot, or dark matter cannot made out of charged particles or out of the elementary particles we know of. So as I said, quarks and electrons are the basic building blocks of our universe, but these are the only one. There are many other fundamental particles. Like by fundamental, I mean you cannot break these particles anymore. Obviously, they can decay, like decay of a big particle into a two different particle. So possible, but these are known as the fundamental particle of our universe, and whatever you can see or whatever phenomena you know, that can be explained by the interaction between all these particles. So they are called quarks, leptons, something called gauge bosons, Higgs boson. So many of you probably heard, like 10 years ago there was a discovery of Higgs boson, and that completes the story of this particle contained of the known universe, and this is known as the standard model of particle physics. But the dark matter, as explained, you cannot consist, or dark matter cannot be made out of these particles we already know. Otherwise, we already have detected dark matter. So then what is dark matter made of? Now the honest answer is we don't know. We don't know what is dark matter made of, but there are different techniques to find out the basic constituents of dark matter. And scientists use three different techniques for that, as I'll explain. So as I said, so it cannot any electric charge. So it's uncharged and under this. It does electromagnetic charge. That's it. But what if it has some other form of interactions which we don't know? So if you studied nuclear physics, so you already know that in our visible part of the universe, there are 4 different form of forces, like electromagnetic force, strong force, weak force, gravitational force. We already know that dark matter interacts through gravitationally, so it can feel gravitational force, but we don't know anything else, like any other form of force, whether dark matter interacts with those force or not. So some scientists, or fraction of particle physics who interested in dark matter, they believe that dark matter has some kind of very, very tiny or very, very weak interactions, very small interactions with the visible sector of the universe. So if you want to know a person, the first and foremost, the first thing it will come to your mind that you will directly go to that particular person and start talking and try to gather more and more information about the person. So that's possible if you have the possibility to know that particular person, and if you already have some idea where he or she lives, what he or she does, so you can go and directly try to talk to him and you can try to know that particular person. But what if that's not possible? What if you don't have any idea where that particular lives, and how exactly you can try to find out about that person? So what you will do, you will try to find a common between that person and you, and then you will try to ask many questions to this guy about the person you want to know. So, but there is a third possibility nowadays. So, if you, let's suppose you don't have any common friend between person and you, but there are many other ways you can find out some information, which is, I mean, which are like social medias like Facebook, Instagram, LinkedIn, Twitter. You can use anything depending on what are the information you really want to gather, and that's how you can out about that person, what he likes or what he or she likes, what he or she does, or how, I mean, anything about that particular person. Which, of course, condition is that he or she have to put those informations into Facebook or Instagram or into something. So these are the three ways you can try to find out about the particular person you are interested to know. So here also scientists use the same three techniques to know about dark matter. So the first process, go directly to the person and talk to him or her, is known as direct detection. So what if dark matter some non-negligible interaction with the, or what if dark matter talks to the visible sector of our universe very weakly, but not weak that we cannot, our experiments cannot detect those interactions. So if there is some form of force which we already don't, which we don't know yet, but theoretically you can build many different form of forces and try to detect them or try to check your from these observations. So there it is believed that if there is a connection between visible sector and dark matter, so you can build some experiments in Earth. Basically, you can it works like you have a target material. I believe that the many dark matter particles are passing through Earth every. I mean, almost now there are many dark matter particles are passing through Earth, passing through even. So if we can build a very sophisticated experimental technique, experimental setup, and we can put a target material, then as I'm saying, the dark matter particles are passing through that target material. It can hit that target material and give you some or inject some energies into that particular experiment, into that particular target. And then if you see some deflection or anything, I mean, that depends on your experimental techniques. So if you can find something information, it can be in form of different kind of energies, but if you can find some form of deflection target material, so that will give you some information about dark matter. So it's kind of a direct interaction or direct. So dark matter comes to your experiment and to you. So it's kind of direct detection. But the other two techniques, like you have some mediator between you and your friend. So these two techniques are called collider and indirect detection. So you can, as I've already said, 10 years ago, there was a discovery of Higgs boson, which was the completion of something called standard model of particle physics. So you can also try to create those particles in a similar fashion we created Higgs boson 10 years ago. So that works as collider. Like you have two protons which are colliding between themselves and generate many. And now, as I am saying again and again, so it's a possibility that there can be a connection between dark matter and visible sector. If it's there, then you can produce dark matter particles in the collider exactly similar to the way you have produced Higgs boson 10 years ago, or you have discovered Higgs boson 10 years ago. And there is also a technique called indirect detection. So it's similar to gathering information about someone from social medias. So indirect detection works in a way that you have many telescopes nowadays, like Hubble telescope, James Webb telescope. There are many very sophisticated telescopes. Now, if you have a telescope, you can directly look at the sky and observe different kind of phenomena. You can collect different photons or different lights coming from different directions. Now, as I said, light can interact, or light can be bent because of the presence of heavy massive particles. So by detecting those lights from different part of our sky, you can gather some information about about the route it's covered from the source to your telescope. So most of the objects nowadays we can observe it can be located far away from us. So now some light which was emitted from that object which is located far away, so it have to cover a long distance from that object to the telescope, right? So it have to pass through a long distance, and this whole space is so far as we know, this whole space is filled of dark matter particles. By detecting those photons, or by gathering those lights, you can find out some information about those, because the presence of dark matter can increase the number of photon or amount of light you are gathering from a particular direction. Like, let's suppose you are looking directly at the center of our galaxy or any galaxy. Now it is believed that our center of our galaxy, or center of a galaxy, in the center of the galaxy, a large chunk of dark matter present. Actually, part of dark matter is concentrated at the center of any galaxy. Now, from there, they can basically annihilate, and you can detect them through the telescope and gather some information about the new form of interactions of dark matter. And now there are different experiments, as I was explaining, which are dependent on the first method, like direct detection of dark matter. There are many experiments which are trying to detect dark matter from different perspectives. Some of them dependent on the recoil of a target material. Some of them are dependent on transition from one atomic energy state to another atomic energy state. Some of them depends on superconducting materials. So there are many different techniques scientists are using to detect dark matter. And so far, all these experiments, they could not find any features of dark matter, but they tells you that basically the interaction strength, or the dark matter talks with the visible sector particles, are not really strong. If this conversation between dark matter, the visible matter, if this was strong enough, we could have already detected those particles by this all these scientists have planned or taken data from. Now this is the last slide. So I just wanted to show, if you try to understand the history of our universe, and if you just write it in a Google that you want to know the history of our universe, this is a compulsory picture you'll find. And the horizontal axis is it represents time. The different slice of this cylinder is a screenshot of our universe at different times. So if you go back from today to the beginning of our universe, you have to go from the right side of the plot to the left side of the plot. Now, the present day universe is the rightmost slice of this particular cylinder. Now, how much dark matter is exactly there, you can also, as I was explaining from these three different observations, can tell you how much total mass was there, because the velocities, the lensing, all these things depends on the amount of mass you have. But you can also gather some information about the total mass of total amount of dark matter from something that is known as or more interesting, you can gather some information about total amount of dark matter from some light again, which is coming from almost at the beginning of our universe. So this green line, you can see that this slice is known as cosmic microwave background. The word cosmic microwave background, the idea here, this in this telescope, scientists have observed some light which has come from this to this distance, like it's from 13.7 billion years ago. So we have observed some light which has come from 13.7 billion years ago. Now, those photons which are coming from such a long time, I mean, which were emitted or which were like traveling for so long time, that tracks some information, or that brings some information about the total amount of dark matter. So what I'm trying to say is, if you have different amount of dark matter in the universe, so this, along with this green slice, this whole picture will look different. So the existence, or the reason we exist today in the form of the form we see today of our total universe, that is very much dependent on the amount of matter we or the universe has started with. So if the universe was started with a different amount of dark matter, so the whole universe we see today, that would look completely different. So the form of all these planets, galaxies, human beings, whatever you can see, so this whole form obviously depends on how much dark matter we had in the initial time. Now, so far I was explaining that it have to be a I mean, dark matter have to be a particle, because we are familiar with the form of matter which are particle, like electron, proton, neutron. All these things are different form of particles. But I'm not going to the details of any technical things I'm doing, or many other dark matter physicists are doing. But it's not. It's simply a possibility that it can be a particle. So many other studies where people believe that it can be a different form of black hole. It's known as primordial black hole, or it can be, there is also other theoretical explanation. Something is known as modified gravity, so you can change or you can modify the theory of gravity you already know, and then you can to explain all these phenomena I have observed. And different theoretical explanations have different pros and different cons, but all of them are possibilities, and none of these theoretical models are not really established true theory of dark matter. So there are many different possible theories, and people are still looking for dark matter particles in different experiments. So maybe maybe in near future we'll detect dark matter and we'll gather more. I mean, we'll know more and more about dark matter particles, whether it's or whether it's a modified gravity, or whether different kind of theory. So we will know. I hope we will know shortly. Yeah.
Are you done?
Yeah.
Yeah. You for your excellent talk, Dr. Nanda. So we can start the question answer session. So you actually explain very non-trivial things in very simple words, so that our student can understand. And I'm sure that they have learned a lot. Also, few dark matter experts, I mean, who have worked on dark matter, are also present in our participant list. So question, or otherwise you can also type your questions or queries in the chat box. Yeah, there is one question. How astronomer measure the mass of galaxy?
Okay, that's a nice question. So I think I don't have here. Okay, so mass. I mean, there is a word called luminosity. There is a observable called luminosity. So luminosity means how bright a star or a astrophysical object is. So the more mass an astrophysical object have, the more luminous it will be. So from by calculating or by measuring the luminosity of an astrophysical object, you can calculate what is the total mass of that particular object. So there are techniques by which you can measure the luminosity, and you can obviously the other parameter to measure the distance from your telescope to the object. So if you have these two information, like the total luminosity and the you can calculate the total mass of anything. It can be a galaxy, it can be star, it can be anything.
Yeah, any more question? You can directly unmute yourself. So there is one question. What is dark matter? How can we experimentally detect it?
Okay.
I think yes, you can still.
Yeah. So okay. So let me just try to explain it. So let's suppose I think I have the just a second. Yeah. So can you see the this image? Yeah. So as I say, the whole space around us is. So the first thing is that the first assumption is that we have to or dark matter have to consists of particles. Then only the techniques I have explained they are applicable. Now, if you say that dark matter consists of particles, and then the whole space around us is filled of these tiny dark matter particles, and they are passing through Earth. I mean, they are passing through Earth, and now the idea is so if you build an some experiments here, and now these all these dark matter particles are passing through your target. What can happen? You have a electron or a nucleus here, and these dark matter particles are coming, and it can hit. Sorry, it can hit the nucleus or electrons, and then you can see. So your target is at rest. This dark matter particle comes and hits the target material, and then this it can move the target material. It can basically shift the nucleus or electrons from its rest position, and you can detect those particles here, and then you can gather some information about this collision, like how much strength it has or how much energy it has transferred from dark matter to this nucleus or electrons, and that will give you some information about the dark matter. As I said, it's direct detection, but there is other technique which is known as indirect detection and collider. So what you can do, or what can be done, is that in colli there is inter or there is an experimental setup known as Large Hadron Collider, where different or huge number of protons basically collide between themselves and produce many new particles. By new, I mean which can be produced. I mean, the theory have to allow those in those productions. Like you cannot produce anything you, but those number of particles can be produced which have interactions with these protons or with these quarks or the visible sector. So now, if you collide two protons with a large amount of energy, and then you already know the most famous formula of Einstein, like E equals mc square. So this energy stored, or energy which was stored in proton beam, that can be translated from kinetic energy to the mass energy, and you can produce many particles during this in these collisions. So now, as I was, if there is a connection between visible sector and the dark matter sector, then this collision can produce those dark matter particles in the experimental setup, and you can detect those particles. And there is another way which is known as indirect detection through telescopes. Also, you can gather information about dark matter.
Yeah, I think this nice explanation can explain his query. And there is another question: at what time in the Big Bang theory dark matter appears? I think he's asking about the time scale at what dark matter particles are formed. Really?
So, I mean, it's okay. It's a very nice question. So dark matter particles, I mean, it depends on theories, what kind of theory you are proposing, or depending on different kind of theory, you can produce dark matter at different time. But there is a timeline that before that you have to definitely generate dark matter, which is this green patch. So dark matter have to be definitely produced before this timeline. So you cannot produce, or any theory cannot produce dark matter if it's obviously if it's a particle, then it cannot be produced after this formation of this green patch or green blue yellow patch. So that's the idea. So dark matter definitely have to be produced like 13.6 billion years ago. Otherwise, this will, I mean, because we have already observed this patch, if dark matter was not there, then this patch would look completely different. So yeah, that's a one line answer, I guess. But obviously, depending on different theories, it can be produced at different times.
Yeah, there is another question by Gagan Yavansi. What was the dark age after Big Bang?
Okay, so this formation of this green patch, and then there is some gap which is known as this dark age. So after this dark age, you can see light, right? This the visible or the form of light we are familiar with. So this time between this green patch and the formation of the fast star, so this is the time in this form. I mean, in between this, like the formation of this green patch and then the formation of the fast star of the universe. So because before formation of the fast star, you could not see anything. So that's this dark age. I mean, there was nothing, only the photons and some form of light elements like neutrons or heliums. this kind of particles. So that's why you cannot see anything in this patch. So this is known as, that's why it's called dark edge.
Okay, so another question is by Gagandeep. He is asking, does understanding weak interaction window for study about dark matter, or what are the ways we can study dark matter?
Sorry, can you just repeat?
Yeah, he's asking, does understanding weak interaction is a window for study dark matter, or what are the alternate ways to study dark matter?
Okay, that's a really nice question. So
Yes.
again, it depends. I mean, there was, I mean, like 10 years ago, 10, 15 years ago, I mean, scientists really believed that dark matter has some kind of weak interaction. There is a phrase called WIMP, weakly interacting massive particles. So they believe that dark matter really has weak interaction, and it interacts the same way. If it was correct, then we already would have detected dark matter in these experiments I was showing. So obviously, the interactions dark matter have with visible sector that have to be much weaker than the weak interactions, or it has some other form of interaction. There are many different models particle physics. And now from the detection, I mean, what was the second part of the question? The detection of something.
So he's asking, what are the alternate ways, I think, we can study
You mean
dark
the
matter?
theoretical part of dark
I
matter?
think so. Gagandeep, you may also unmute yourself and discuss.
Sir, experimental way we can study the dark matter.
Yeah, I mean, these are the experiments which are interested. I mean, to detect dark matter, you have to have some interactions, or I mean, the dark sector have to talk to visible sector. So there are different experimental techniques people use nowadays. It depends, as I said, it depends on recoil energy. It depends on atomic transition between different energy levels of an atom. It depends on superconducting materials. So, oh, sorry, semiconductor materials. So there are different techniques I mean, scientists use, but so far we did not or could not find anything. All these experiments gave nothing about dark matter. And we have to, I mean, you cannot build something, or you cannot build a new experiment with a new theory, right? So you have to, I mean, you can only build new experiments depending on what are the known theories you already have. So that's the main problem to detect dark matter, because we have no idea whether it really has any interaction with the visible sector or not, except gravitationally. So all these are the possibilities, like recoil of a particle, transition from different energy levels. So that's how all the experiments have been set up so far. But yeah, nothing is discovered.
And another
Nowadays,
question.
oh sorry, last line. Nowadays,
Yeah,
we are
yeah.
also trying to detect dark matter from gravitational waves, and there are other forms matter or other theoretical possibilities of dark matter, or maybe there's a way of cosmological signatures of matter, but they're all depend on what kind of theoretical setup you have, and depending on that, the signatures can be different. So obviously, there are different studies or different works. I mean, is going on to gather more and more information about dark matter.
And there is another question by Sandan Kumar. He is asking, is there any information about the mass density profile of dark matter in the universe?
Yeah, it's a nice question again. Yes, there are obviously there are different density profiles, which So again, the density profiles are theoretical proposals, and the observed universe, we see that different part, like large scale, small scale, depending on what kind of scales you are interested to explain, the different profile matches with different observations. So there is not a, I mean, there is not a fixed distribution of density or fixed density profile which is established as a density profile. But there are many density profiles, and it's not fixed that which one is exactly the correct density profile.
And Bikram Deka is
Hello, Divyendu.
yeah, yeah. You may go ahead. Yeah.
Although the scientific community generally accept the dark matter existence, but there are other theories as well, like modified
Gravity,
electron and
yeah.
dynamics.
Mm.
What are your take on that? Because these theoretical concept totally discard the non-baryonic matter. So what is your take on that?
Okay. Okay. I mean, I don't know. I mean, details about this modified gravity or particularly, I mean, this theories which depends on modification of gravity. But as far as I know, so community of particle physics or the community of cosmologists, they're interested in particle nature of dark matter because then particle dark matter can only explain these three observations. Like the modified gravity can explain the first one by Zwicky, or the second one by Vera Rubin. But it's, as far as I know, it's really extremely difficult to explain the bullet cluster, the third observation, by using modified gravity. So the idea is that a theory, I mean, you can build a new theories, but that also have to be consistent with all the observations we already have. So the dark matter, or the particle dark matter, is the only solution so far which agrees with all these different observations. So that's why community of particle physicists was so much involved in the particle nature. But I have honestly, I have no idea about modified gravity.
Yeah. Okay. Thank you.
Yeah.
Yeah. Bikram Deka is asking what is the difference between dark matter and dark energy.
Okay. So the one-liner difference is that dark matter is a form of matter because it interacts gravitationally, or it behaves like a matter, like the equation of state and everything. But dark energy is, I mean, again, the information about dark energy is only from this picture, and yeah, is it only from this picture? But it does not behave as a matter. So that we don't have any, I mean, apart from the amount of dark energy we have, other than that, we have no idea about what it is. So they're completely different. Is established that it's a matter, and other behaves in a way which is not matter, which is not radiation, which is completely different. And there is, I mean, there is very less amount of information about dark energy than the dark matter. Obviously, there are many studies, many models of many cosmological models of dark energy, but yeah, basic difference.
Yeah. So are there any more questions? Yeah, there is one. Jannatul is asking, sir, earlier people believed that nucleons are the elementary particles. Then how the picture of quarks to highlight, telling these nucleons are made up of quarks?
Oh, wow. Okay. Okay, so that's that depends on, so okay, so can I explain easily? So it's, so if you want to break a house, right, or break a building, what will you do? I mean, if a whole building is there, you don't know what is this building made of, so you need energy, right? You have to break those break the building, and then you can find out, okay, so it's made out of bricks and something, and then you will go on and break bricks, and then you will try to go as far, I mean, as small as possible. Then you will find atoms, right? So that basically means it depends on experiments, or it depends on the available energy of the experiments, or it depends on your strength whether you can break the or not. So initially it was, so if you know the binding energy of an atom, it's electron volt order, but the binding energy of a nucleus is MeV order. Now there's increment of this energy, right? So the experiment, that's why it took time to go smaller and smaller, because as you go smaller and smaller, you will need more and more sensitivity, more and more energy to go into that particular system. So that's how it progressed. So first we understand atom, then nucleus, then neutron, proton, then quarks.
Yeah. So there is another question by Sandan Kumar. Is quantum gravity is the next step in understanding dark matter?
I don't know quantum gravity. Sorry,
Yes.
I don't know.
Okay. So is there any more question? So it's very good that we have a very good discussion session. But if you have any more question, you can still mute yourself or type the question.
Yeah, but frankly speaking, when I was an undergrad student, I heard
Yes,
about
yes.
dark matter. So maybe
Yeah.
it
Yeah,
will
that
be
is the thing.
familiar
I
to you.
mean, our students are very fortunate, and we are also thankful to these online
Yeah.
platforms so that we can bring the researcher in front of our undergraduate and postgraduate
Mm-hmm.
students. And also, our idea is fulfilling because many of the students from outside Assam are joining our talks. So, very good sign
Mm-hmm.
that we could bring everyone together. And also, thanks to you for, I mean, despite of your busy schedule. Also, I want to let my students know that Divyendu was my senior while I was doing PhD. So I learned a lot from him during my PhD at IIT Guwahati. So
Anyway, thanks for so many questions, interesting questions.
yeah. So are there any more questions? If not, then we can thank the speaker. Okay, let's thank the speaker for his excellent talk and discussing these things in so much details. I think the participants would learn a lot from him. I also learned a lot. And let's close the session then. I would now like to request my colleague, Dr. Dipsika Gogoi, to end the session by her closing remarks and a vote of thanks to the speaker. Dipsika, are you there?
Devabrot?
Yeah, you are good.
Yeah, you are good. Okay, okay. So, on behalf of the Department of Physics of Abhayapuri College, I would like to thank the speaker today, Dr. Divyendu Nanda, for this very interesting talk on quite an interesting topic. And I guess all the participants are benefited from his talk. And also today it seems to be a mixed category of participants from undergraduate to postgraduate to PhD students, I guess. So I hope everyone enjoyed the talk, and especially our students who are by now at least familiar with the term this, so that whenever they hear these terms in future, they can at least connect and understand something. So I would like to thank the speaker again, and also all the participants, including our students and participants from outside, for making this session very interactive and successful. So on this note, I would like to declare this session closed. So thank you everyone, and thank you Divyendu.
Thank you.
Thank you.
Bye.
Okay.
Yeah.
Thank you.
Bye.